Welcome to the workshop, and today I take some pressure off of my plate. Well guys, thanks so much for tuning in for this episode. I'm really excited to share this with you. I have today here a very custom piece of kit. This is a mostly it's an Arduino Nano. And as you can tell from the title of the episode, this is a pressure sensor. Something that I had an idea about a bit over a year ago and thought this would be something absolutely fantastic. So let me explain first what it is, why it is, and then I'll get more into the how it is. So what this is obviously it's a telemetry sensor, okay? Now, and going a little bit deeper than that, it is a sensor for FrSky telemetry protocol that senses pressure. And what I essentially have is an Arduino Nano that has some code loaded onto it, and I have a smaller prototyping board from actually from my local hobby shop. They sell Radio Shack parts of all things. But then I have an actual pressure sensor that I bought separately, and through just a couple of wires and a single resistor, I have a working telemetry sensor for pressure. Now, in addition to specifics of this, this is powered off of the receiver. There's no other power that needs to go to it, and it is able to sense from 0 all the way up to 150 psi. What that is good for is we're getting into the what now. What this is. We can sense pressure with this up to 150 psi so that we can keep tabs on essentially how full a pressure tank is for a pneumatic retract system. Now, why would you want this? Pneumatic retract systems have been around the hobby a very long time. There are multiple different types. Specifically, we're talking about types that automatically spring down. So if the valve is switched, so the way for those that don't know, the way that they work is there is a servo. Let me pause here for a sec, get some, I'll be right back.
1 minute, 37 seconds later.
All right, so this is a retract valve. Well, it doesn't necessarily have to be for retract, but it is a pneumatic valve for RC. It is made by a company called Robart, and the way that you hook it up is there's this screw here. You'll have a flat wood plate or whatever plate within your airplane that you will mount this to, and then there is a servo that connects to this piston. And you can see this end here. And when the servo moves, it moves the piston from one end to the other. And that is literally all that it does. It's essentially a switch for a pressure system. And there's these little tiny hose barbs on it that connect the pressure system. And these knobs on this specific model of valve, you can regulate how quickly the air goes in or comes out through the pressure system. Okay. That being said, with some retract systems, when you have the valve in a certain way, it loses pressure to the air piston that's on the retract that pushes the landing gear down or landing gear up. When that pressure is lost, there is a spring that automatically flips them down. Pretty nice in case you get a pinhole leak or a burst on the line of some sort. But the problem is that you can't really do more scale airplanes, particularly ones that have gear doors, unless you get into really elaborate mechanical gear door systems that can be finicky and an absolute nightmare to set up. So what they also have are non-spring air type, where you have the piston that has pressure on the piston to make it go down and pressure on the piston to make it go up. And those are the type that I plan on using for my P51 Mustang build. Now, the problem with this is that should you get a leak or you have some sort of failure in flight, you will not know until you try to put the landing gear down. I have seen many times when people don't have a catastrophic failure. Most of the time, it's some sort of leak. And the reason that these leaks generally happen is that you have the airplane sitting on the ground in the pits and you pressurize the system with air. You use an air compressor, whether it be a hand pump or something electric, and then the airplane goes out in the sun and it flies around. It's still getting hot and it's still heating up the air inside that pressure canister, so it expands more. So what could start out as 100 psi could go up to 120 psi. Well, you think, well, wouldn't you test your system for that? Well, sure, but you can only test in a sort of static environment. When you're flying through the air, there are all sorts of oscillations and vibrations. It's a much more dynamic system, so testing only gets you so far. That's why some of these failures happen. And what this failure is a slow leak. And so when you go to land, you don't have enough air to get the landing gear down. That's where this comes in. By having a telemetry sensor within my radio, I can set it to have an alarm so that your landing gear is on a switch. If I have a telemetry sensor, I can, in my FrSky radio, program a logic switch. Okay? A logic switch. And I'm going to get a little bit into that. This is going to be a technical episode. It's going to be a little bit long, so hold your horses. The logic switch will override the physical switch, and it can automatically sequence the inner gear doors to come down and the main gear doors to the main gear to extend. That is the advantage of this, because I can set a certain threshold of pressure for it to automatically deploy. The reason, there are two things for this particular project why I wanted to develop this. Number one, safety. The Mustang is going to have this custom motor setup thing on the front of it, and because it's rotating in such a way, I don't want to have a prop strike or anything as a result of not having landing gear down, because it can send parts flying, and it can send parts flying into people. And so if I can avoid that, I'm going to. Number two, if that were to happen, I would also potentially lose the plane. Again, lots of little parts that can come off on a belly landing that can go back and beat things up, whether it be the belly scoop just by grazing across the ground, or something comes off and rips into the wing or the H-stab. There's lots of parts on the front of this airplane, and I want to be able to preserve the airplane, so this is insurance. This is a piece of insurance. Now, getting into this, I'm going to go over some things, but first let's put a little video of the basics of how this entire system works. Here's a little clip. Okay, I'm going to try to explain this in the simplest possible way. I have a receiver that is talking to my transmitter right here. I have a servo set up to simulate being on my landing gear, gear down, gear up. Okay, so that's working just fine. This is a telemetry sensor that I have made with the help of our wonderful RC community. It measures the pressure of the pneumatic system. So this is my feed line coming from my air compressor. Air compressor says it's just a hair under 80, and that's exactly what my telemetry is telling me. Now, with the gear in the up position, the cool part is when I go to release the pressure and get down to about 60 psi, the gear will automatically deploy. All right, so from there, you kind of have the broad picture of what this is, what it does, why I have it. Now let's figure out how it works and how it goes together. All right, so here is a pretty close-up version look at this whole assembly. So I've got a length of servo wire, and I did crimp this myself with a crimping kit, but you can use any servo extension. So this is the part that will be plugged into your smart port on your FrSky system. And they're the three wires. The signal wire that goes back into the radio has to operate at around 3.3 volts. However, the Arduino and the sensor need to operate off of 5 volts. Therefore, I used a resistor in line with that signal wire, and that's what that is there. This is a 5.6K resistor, and for those who don't know, there is no polarity to resistors. You just put it in line, and that goes directly to my D2 pin on the Arduino. Now, the power goes to, we're going to turn this around. Power, the positive, goes to the 5 volt, right there where it says 5 volt. I also have a ground right there, and that's where the black wire goes. Okay, so now we have power going in, and we have our signal wire going out off of D2. Now, we have these pins come out that connect to this board, and on my sensor, it has a data sheet that shows the orientation, and it's important to note this little dot in the bottom left corner of the sensor, because that gives you the orientation for the pins. Pin number 1, 2, 3, 4, 5, 6, 7, and 8. On this particular sensor, the only pins that are active are pins 1, 2, and 4. Okay, my mistake. Back up here. Pin number 2, 3, and 4 are the pins that are active. Okay, so pin number 2 is your positive. Pin number 4 is your negative, and pin number 3 is your signal. So you get extensions to these pads over here on the top side underneath here with some wires. You can see the yellow for the signal that goes from pin number 3 and goes all the way back to your A7. A7. Okay, so pin 3 on the sensor goes to A7. And so what happens is the amount of pressure that is applied to this port correlates to a certain amount of voltage that will output from pin 3. Inside the Arduino Nano, and this is an Arduino Nano V3, we will adjust some code, and I'll show you how to do that, but it's pretty fantastic since things are open source. There is a project called OpenX Sensor, and you modify the firmware or the sketch in Arduino to make this work the way you want. So with the basic wiring and assembly together, let's go look at the software. All right, guys, so we're here on my desktop, and I'm going to bring up some windows and show you around and hopefully help you navigate some things. So the first thing you're going to want to do is go to the OpenX Sensor website, and you're going to want to download the OpenX Sensor download. Obviously, it's pretty self-explanatory. Really what you're downloading is a zip file, and when you navigate to the zip file after downloading, let me bring this window in here, downloads, OpenX Sensor here.
So you're going to be given this folder. So when you open a file, it has to be within a folder that has all the contents. So you're just going to extract this entire folder to like your desktop. And from there, you can open the INO file using the Arduino software. And what that looks like is this. You're going to start with the OpenX sensor tab. It'll open like that. It's a whole bunch of gobbledygook that I really don't understand. So what I'm going to do here is show you, just for referencing, if you're going to be doing this on your own, go to your preferences and make sure you click on display line numbers. That's these lines, and that shows you the line of code that we're going to be referencing. So you're going to want that, and from there, we are going to over here and go to configuration advanced. So what you're gonna look at first, let's go to the top. Okay, so pin serial. Okay, so 1.1, the pin that you're going to connect to the receiver. So the pin which transmits the serial data to the telemetry receiver, usually pin 4, otherwise pin 2. So I set it to pin number 2. Okay, from there, so this is a digital. So this is a D2. D2, not A2 on the Arduino Nano board. Got to specify that, and that's line 20. All right, so then we're going to scroll down to, okay, voltages, section 6. Okay, section 6. So this essentially, this sensor is being treated like a voltage sensor. And in section 6, we're going to set up that voltage sensor. And you can use any of the analog inputs on the Arduino. There are many of them. We are going to use the first column here. You got to think of these commas as like dividers for columns. And I reset all of these. Some were filled in. I just reset them so that they were back to stock. 8, you have options from A0 up to A7. 8 means you're not going to measure anything. Okay, so our first column, we're going to select pin A7. So we have a number 7 right there on the first value on line 126, and then we're going to move down. Resistor to ground is going to be 0 because we have no resistors between our ground and our sensor. We have no resistors between our voltage, our positive terminal, and our sensor. And we're not going to mess with the offset voltage or the scale of the voltage. We're just going to leave those at 1. Mostly because we can adjust these in the transmitter, and it's a whole lot easier to adjust this in the transmitter than it is to adjust it on the software and then, complete compiling it and uploading it. I mean, it's kind of a pain to go back and forth. You just set it once and you're done. At this point, everything else is pretty much set the way you need it to be. All right, so another thing that I need to mention at this point is that our offset voltage and our scale voltage requires a reference. There's a couple of different ways that we have this reference. The reference can be the voltage that's coming in, and so I mean ideally that would be like whatever your BEC or from your the built-in BEC for your ESC, whatever voltage is coming in, it's going to be that voltage, or it's the reference voltage that goes through the Arduino. So the Arduino regulates its own voltage a little bit as well. So it could be that voltage. With the reference voltage, you can set the reference. With the reference voltage, it's still here in section 6. I had forgotten where it was because there's so many lines of code here. So yeah, your internal. So normally by default, the sketch wants you to reference the voltage of the Arduino as the voltage is coming in. Okay, so for example, this line 121, define use external reference. Uncomment this line if you use an external reference instead of VCC, which is your voltage in. So you can uncomment that line, define use external reference, and it'll use an external reference, which will be this line. So you set the reference voltage. So you would have to uncomment these two lines in order to do that, and you would say, okay, so my reference is this voltage. So I could actually do that because I know what my voltage is. I am going to be using a BEC, and it does regulate the voltage pretty well. So I could set this for 5000 because that's in millivolts. So that would be equivalent to 5 volts. But as it is, I'm just going to be using the normal voltage in, so I do not need those uncommented. So those forward slashes, those are the comment, and that's how you do that. From there, make sure that you have your Arduino connected by USB, and then you go to the upload. And it'll compile everything, and it'll throw errors if there's anything wrong with it, but if you've just modified those few lines, it'll be just fine, and it'll tell you when it's done, and you can disconnect it and then try it out. Now, while I have you here, I also want to show you the sensor that I got. I did buy it from Mouser, and this is the exact sensor that I got. Mouser number 785-SSC-DAN-T150PGAA5, which corresponds to the manufacturer part number as well. Anyway, what's really cool is that you can see the data sheet. I know DigiKey does this as well. The DigiKey and Mouser websites reference the data sheets from the manufacturers. In this case, it's Honeywell, Go Garrett Turbos. So we have this sensor, which the whole series can be digital or analog. We have pressure capacity, we have standard accuracy, compensated or amplified, all sorts of different things of this entire line. And there's lots of different options that you can select, and those options are determined by the number in the model number. So these are standard parameters for all of the sensors. 5 milliamp draw. Temperature operating range, compensated temperature operating range. So we could do this in really, really cold, and we can do this in very, very warm. So again, it's going to automatically compensate for temperature and response time, those kinds of things. These really interesting statistics and performance parameters, which are awesome to know. But it comes down to the numbering scheme, which is here. So based on this is the series, the SSC series, dual inline pin, and then all of these numbers add up, and we're looking for the 150 PG, 0 PSI to 150 PSI, again, 150 PG, and then AA5, whatever those numbers mean. Now, what's really great here is that in addition to having all of the statistics, we have these transfer function charts, which are totally awesome and help you understand how this works. So if we have, we're going to get an output if we have the voltage that we're going to put in, and we're going to have the minimum pressure and the maximum pressure of the particular part. So in this case is 0 and 150, and then the pressure applied, and then the P minimum, which is 0, and then again your voltage supply. So we can plug in all of these parameters and spit out an Excel spreadsheet and get an approximate output voltage, and that's essentially what you're seeing here. is your output percent of the voltage supply, and that corresponds to your pressure. So it's pretty linear, and if we wanted to get really super clever, we could actually incorporate this math into the sketch, but I'm not that clever, and frankly, I've got enough control and sensitivity within the transmitter as it is that I didn't really feel like I needed to go down that rabbit hole, and you'll see what I mean once I get the transmitter going. So, one thing to also note is down below, you have your different models with their pins. I showed you like the little dot that gives you the pin indicator. In this case, we have this style. So we had the little dot that shows you the orientation, pins 1, 2, 3, 4. And then way down here, we have the pinouts of what is going on. So depending on your package, it shows you what your outputs are. So for example, we've got pin 2, 3, and 4 on ours because we've got an analog. So we've got the voltage in, the positive, the voltage out that goes back, and we're measuring that voltage, and we've got our ground. Okay, so those are the things that you're looking for, so you know what pins to use. So if you select a different pressure sensor, those are the things you're going to want to look for. All right, so let's get off the desktop and go to the transmitter.
All right, here we are on the bench. So I've got my tripod here, and I'll show you a little bit around. I've got my setup here with my source battery, my BEC, my receiver, a test servo, and the unit itself. Got some pressure over here, as well as a pump. It's a hand pump. So let me just position this tripod right, because I don't want you to get any glare. So that's bad. You can't see that. All right. So first thing I'm going to do is I'm going to plug in okay.
RSSI critical.
Yeah, that's because I'm close. All right, so now I'm going to get stuff going in and out, so I want to move this so that I get it all the time. All right, so my test servo is working, and I'm getting my BEC voltage. That's coming from one of the FrSky Neuron SBECs. Those are pretty new. That has built-in telemetry and tells me my source voltage that way. I have tested with a multimeter, and it is 5.0 volts on the Arduino and the pinouts. So the first thing you want to do is go into your model, and I long press backwards once to go into telemetry right away. And when you're first plugging this in, you're going to scroll down until you see the Discover New Sensors, and you're going to do that. And then for me, this A3 showed up. So what I did was I went into the A3, and it is a custom one. It defaults to custom. And the source is internal module and unit. I specifically selected no unit because there is no option for pressure. Precision, this is the number of units, so we can go like what the readout says, 11.94. There's a reason for the 11.94, and I'll get there. So here, the same ratio and offset that we saw, you can modify that here. And what I did was I changed the offset. So originally, when I first plugged this in, it was reading at -5 volts. Which I thought was weird because I expected it, based off of that equation in the transfer function sheet, I expected it to be 0.53 volts. Weird, but there it is. So again, we adjusted it to zero it out. And then I started playing with the ratio. Now, what I did to play with the ratio was I took my pressure pump here and I pumped it up until I got to 40 psi. So I did that. I'm going to do that now. see the pressure going up. All right, so my pressure is reading about just a little bit over 40 psi, but here it's reading at 47. So a little bit higher on this gauge. Now, this is not a calibrated gauge, so I'm not saying that this is absolute gospel by any means. What I'm saying is what is critical? What is the number that is critical on my transmitter? And that is the 60 psi mark. All right, so we are just above 60 on the transmitter, and we are just above 60 on the pressure as well. So that's really my gauge. If I were to go all the way up to 100 psi, it would be the pressure here would still be a little bit above 100 psi. You can continue to play with the ratio to sort of dial things in. Again, I'm not looking for absolute numbers. Sure, that would be nice. But really, this is primarily to function as a fail-safe. All right, so the 60 psi is the critical one. Now, how do we get there? I'm going to long press. Let's go back first. We're going to long press back. We're not doing custom scripts. We're not doing special functions. So we have the gear up and gear down. Actually, I'm gonna take this test servo as a demonstration and put that on what I think.
Gear up, gear down.
Yeah. Okay. So let me move this over so that you can see that.
Gear up.
That's my
gear down.
gear up
Gear up,
and gear down.
Gear up, gear down.
So this would be that servo that's on that valve that would go back and forth. Okay. So looking here at my logic switch, A is greater than X, where A being the input of the pressure, or sorry, A is less than X, where A is the input, and if it's less than 60, you want SG, which is my gear switch, to go down.
Gear up, gear
So
down.
that automatically
Gear up,
will
gear down.
override my physical switch. And to see if this works, I am going to depressurize my system by just unplugging it. And I'm going to let you watch my pressure at 65. As soon as it gets to 60, it's going to drop that. Oh wait, I have to put it
Gear up.
in the gear up position. See? And that's how you do it. Now, with that, I can go in and program curves. So based off of timing of a curve with my gear doors, I can override the gear doors and the landing gear all in one fell swoop. And that's how you program the radio. It's really quite straightforward. It's one logic switch, and you set it up, and that's it. Really quite nice. Now, with that same kind of logic switch, again, going back, so I can program a logic switch to be if A is less than 70 psi or even 80 psi, I can have it do a different logic switch, and then I can go into my special functions and assign a special function to say pressure warning, and I can record my own voice to do that and put that in the radio to do that. I've done that before with my canopy open and canopy closed on my Corsair, which is really, really nice. You can customize this as much or as little as you want. There's so much power in these radio systems that we can take full advantage of it, and it's not a burden at all on the radio. With that said, this is just a very basic overview, and it's something it's a foundation. Okay, I'm not saying this is the way you have to do it. There's a million different ways to do everything in OpenTX, but that's how I've got it set up here. All right, guys, so I'm going to level with you. There were a couple of additional things. I know this is already a long video. I'm already in the process of editing it, but there are a couple of things I did leave out that I need to go over. Okay, so first, why are we seeing discrepancies between the pressure at baseline? So at baseline, the radio is reading, about 12 psi, and matching psi when the pressure gauge from the pump is reading at 0. Okay, so there's okay, so normally the way that scientists, I'm putting on my scientist hat here, okay? When you read pressure, it's measured in atmospheres, right? So there's a layer of the atmosphere, and we experience that pressure. It's about 14.7 psi at sea level. The higher you go up in elevation, the lower that pressure becomes. So where I live, it's about 300 feet above sea level. So that translates to 14.5 psi. So you lose 0.2 psi. So again, it's going to be different from one location to another. So if I go to the Rockies, the elevation is going to be different. So the pressure is going to be different. In addition, you have weather systems that move in and out. Because of where I live, it's kind of swampy. We have been having a lot of rain lately. So when a storm comes through, it's a low pressure system. So you have that influence as well. So that's why you're seeing these discrepancies in pressures. When I originally set up the transmitter, that's why the pressures no longer match, because different weather, and there's a lot of environmental factors that go into it. So in addition, the reason that you have the baseline being offset from what's on the pressure gauge is that the pressure sensor measures absolute pressure. So you have to be in an absolute vacuum in order for it to be at 0. So I'm still kind of playing with it to see what the offset does. So I could offset it plus that 14.5 psi, give or take. But again, the offset is offsetting voltage, not pressure. Okay. So then when you're scaling the voltage, not the pressure. Okay. So again, getting into some of the mathematics and the problematic situations, getting the target 60 psi is what is key. And that's why I say, these are all relativistic kinds of notions. And nothing here is actually calibrated. Okay, the pressure gauge on the pump is not calibrated. The little sensor is not calibrated in any way. So again, we're working with relativistic numbers that are close enough for what the intended end use is to be. We're not using some sort of scientific instrument. It's all relative. And that's really what I want to drive home. Okay, so one last thing I have to take care of. All of this setting up would not have been possible. So I just went through all of that setup, and you guys know that I don't know everything, and I am the first to admit that. And so first and foremost, I have to thank a very special guy. The special guy that gets a good chunk of my gratitude is username Carbo on the OpenRC forums. He has been very, very helpful to guide me through the sketch and get me to the point where I was comfortable. And he also helped me with some of the schematic work, but a lot of the assembly that was helped by Crafty Dan Cruz on the flight test forums. Fantastic guy. I know he knows his electronic stuff. He helped me through some of the initial setup with the Arduino because I didn't have the right drivers. Yeah. Anyway, big shout out to him as well. By far, though, the biggest credit goes to the OpenX sensor team. And the guy who developed that initially is mstren's username. I have no idea who this guy is, but thank you so much for putting all of this together, because otherwise we wouldn't have it. So there you go. Giving credit where credit is due. All I did was take the little pieces of the puzzle and stick them all together. So let's get into some final thoughts. All right, guys. Well, that'll about do it. You've got everything that you need. I'm not an expert. Me and code are like, we don't go together. We have never really gotten along. But I have to say a huge, huge shout out to the people over at the OpenX Sensor team. And certainly we have some fantastic results just out of pure friendship. It's wonderful to see. And thank you so much to them. Thank you so much to you for watching and tuning in. I hope that you get some inspiration, some ideas, and maybe you have a different application for a pressure sensor. Now, I will, final note, talk about cost. So the Arduino Nano V3 I was able to pick up off of Amazon for $6. I got a pack of 3 of them for 18, so 6 times 3 is 18, so $6 for that. The resistor, I got a pack of 5 for $2, and then some PCB stuff, that was another $2 at the local hobby store. So $4 there, and then the sensor, that's the bad news. The sensor was $38. Yeah. Apparently being able to handle and measure that amount of pressure is a pretty big deal. It took me a long time to sort out which sensor I wanted. There may be other options out there that you guys can use. The cheaper ones that are like in the $12 range, they usually only go up to about 60 psi, which is pretty much the cutoff threshold. So in my particular setup, I want to have a warning before I get to that point, so that's why I wanted to have a higher pressure threshold. And 150 psi seemed reasonable, especially like if I charge the tank at 100 psi, sits in the sun, might expand up to 120 or so I have overhead. That being said, you know, guys, take it for what you will. I hope you get a great idea and just run with it. This is fantastic progress, and I really wish that more people knew about this OpenX sensor bit, because I think we'd have some absolutely amazing things to add on to our aircraft. So until next time, I hope you guys just dig right in and enjoy this. I hope you tell all your friends about it. Feel free to copy, ask me questions. I can certainly do my best to answer, but I can't give you all the answers because, again, I'm not an expert. I'm a hobbyist. I'm just sharing with you what I've done and what others have helped me with. So keep on working on your models, keep on dreaming, and until next time, make sure you properly pressurize your flying works of art.